Thank you for the introduction. So today I'm going to talk a little bit about my stay in the Arctic. I was up there in Svalbard, which is within the Arctic Circle, and it's a Norwegian archipelago called Svalbard. And I was there in Longyearbyen, which you can see here. And Longyearbyen was actually called Longyearbyen before it was called Longyearbyen because it was established by an American who had a mining company, and he wanted to start mining up there in the Arctic. And that's why he established and founded Longyearbyen in 1907. And now the population is roughly 2,400 people, which means it's the world's most known settlement that has a population greater than 1,000 people. Here you can see a little bit of a map, so you can get a little bit a feeling of the location up there, but be aware of the scale because we're talking about 100 meters. So everything was like within walking distance of like 5 minutes. So you can see the university campus, the student housing, and also the grocery store. So I like to compare Longyearbyen to any village that you will really found in Lower Austria. It is really small. You have like one grocery store, one bar maybe, and you're in the middle of nowhere. We even use the same methods, but I will tell you more about them later. There are a few things though that are different because we are in the Arctic, right? So we have a lot of dangers that are involved with being in this harsh climate. So before we could start our course, we had to take a 3-day safety course where we learned about how to live in this environment. So I'm going to tell you a little bit about the survival in cold climate in general. We learned how to do an emergency camp and first aid. We also learned about avalanche danger and, of course, polar bear safety because we are in a polar bear environment, and rifle handling. And last but not least, we had a snowmobile driving course to get from A to B. So survival in a cold climate. Here you can see the average temperature in March, -28, quite chilly. But be aware that this is only the temperature itself. So this is without taking the wind into account. And with the wind, things can get quite dangerous really, really quickly because, for example, on this random day on March 14th, it was -21, and you can be fine in -21 if you dress appropriately and there is no wind. But it felt like -33 because the wind is really tough up there and it makes things even more harsh. What can happen? There is this phenomenon called frostbite, which basically is a damage to the skin and tissue. If your skin is directly exposed to temperatures that are freezing, so below 0, if you're not wearing appropriate gear, you can even get frostbitten already. And they also in the safety department, they also highlighted how important it is that your body is in its best condition, which means that you're hydrated, that you have enough food, because only being out there without even moving, just standing there is already so exhausting for your body. So you always need to be in your best condition. But in the beginning, we had some struggles because our water bottles were frozen, our food was frozen. So we had to learn all about it. That was the presentation we had. We learned how to appropriately dress. And these are the stages of frostbite. And I experienced frostnip, which is the first stage where your hands already, or for example, your fingertips already hurting. And once you got it, it's gonna last a few days. But other than that, I was fine. Then we also learned how to set up an emergency camp, because even if it's just a 1-day field trip, you never know what happens. You can get yourself in a bad weather situation, for example, or somebody could get injured, or you have an accident, and then you need to act quickly, because the longer you are out without any shelter, and as I mentioned, the wind can be quite rough, the worse the conditions can get, and people can suffer from hypothermia quite quickly, which means that your body temperature drops below 35, and it can get quite critical at this point. So we also learned what to do if this happens to someone and how to appropriately wrap this person to stay warm. Then another topic, of course, avalanche danger. Longyearbyen, which you can see here, is situated in a valley with very steep slopes, up to 30 and 50 degrees of angle slopes. And what you can see in the blue lines, actually, these are the avalanche runout zones, which means if an avalanche were to happen, this is how far the avalanche would reach. And you can see that it is already covering some houses. So it is a quite dangerous place. And what we also learned is terrain traps. So if we are out in the field and we drive by snowmobiles, or if we are out skiing, for example, we should avoid these traps, which are features such as cliffs or gullies that amplify the consequences of getting caught in an avalanche, because you are some sort of trapped in this situation. If an avalanche is coming and you're in this V-shaped gully, you don't really have somewhere to go, and all the avalanche debris is hitting right there. So interestingly, most of the avalanches, or most of the dangers, happen in considerable or moderate avalanche danger, because people feel safe enough to go out, but they usually don't think about it that much anymore if they're out. And often these avalanches are triggered by the person themselves. So we obviously also had to learn how to act if someone gets buried in an avalanche. And for that, we had to wear these avalanche beacons on our body really close, like not on the jacket or something, because everything can get torn apart, but you need to keep it on your body, and you can either put it in search mode or in a normal mode. And then if someone were to be in an accident and be buried by an avalanche, the other people can put their avalanche beacons in search mode, and this electrical signal will lead you to the position of the person buried. And then you have these probes, which are like sticks, so you can verify the depth of the person buried, and then obviously the shovel. Another topic we learned about, polar bear safety. It's really important because the polar bear is protected by law under the Svalbard Environmental Protection Act, which means that we had to learn about these measures if we wanted to go outside of Longyearbyen. It is stated that it is prohibited to lure, pursue, or otherwise seek out polar bears in such a way as to disturb them or expose either bears or humans to danger. It is also stated that necessary measures shall be taken to avoid the danger of polar bear attacks and to ward off an attack without injuring or killing the animal. So if it were to happen that you are in a position where you need to defend yourself, and you need to kill the animal, then there will be a legal lawsuit against you afterwards, because these animals are protected, and it is important that no hunting is happening. But since 1971, there were only 6 fatal attacks on humans by polar bears. Of course, we had to learn how to use a gun in the case of an emergency or a polar bear encounter. So we went to the shooting range, and we got a certificate afterwards, but this certificate was not enough for you to get an actual gun. You had to get the criminal records from your home country, and then you could get the certificate. And we were 20 students, and you can take, like, per 10-person group, we need 1 gun. So always 2, when we were out in the field, 2 people would always carry 1 gun. But which is more important is actually this gun here, which is a flare gun. And it makes a sound that is similar to fireworks, and it can scare off a polar bear. If it's still far away, far away from you, then you can use this one to scare it off. And it is proven that this sound even scares the polar bear more than the one of the rifle itself. And of course, like I just stated, it is never the goal to actually hurt an animal. So I'm gonna try, if it works, to play this video. Probably not. Yeah, but we each of us could try one time to use this gun, and this is what you would have seen in the video. And then we had a snowmobile driving course. I will not go into depth here, but we learned the technical and mechanical things about it if something were to happen, and we also learned how to dig out a snowmobile, because this happens pretty often. So they put it there and they were like, oh no, the snowmobile is stuck. And then we had to try to get it out. So that was fun. The UNIS Safety Center is really specific about the safety of their students, and they have lots of systems and models implemented so that the student safety is always there. And one of these models is the bow tie model, which basically states the before and aftermath of an unwanted incident. So they were all about prevention. They would not send us out if there was a small risk of anything happening that day. For example, because the weather was not stable enough, they would rather not send us than risk anything. Another system, which is also very well known, is the buddy system, which means that within the group, every person has assigned a buddy so that they can check up on each other when we are out in the field. For example, if this person is cold, if this person suffers from frostbite, just checking up on each other. And also it is pretty hard to multitask in -28. It is so hard to concentrate when you're out there. So everybody gets assigned a different role, which they can concentrate on. For example, if something were to happen, one person carries the communication tools, like the satellite phone, another person carries the gun or the flare gun, and so on. And last but not least, before every field trip itself, the people from the safety department came and told us about the dangers at this specific location on this specific day. So they made extra sure that we also knew what was happening on this day. So even if we were just going out for a little walk outside of the settlement, they would come and say, can get colder than expected, so bring an extra layer. And before every field trip, we would need to fill out this HSE form, which means health, safety, and environment. And it works like a clock in, clock out system at work, where we put this at the university, and in the afternoon or evening, someone would check if every group has returned. So after all the safety measures taken in place and after the completion of the safety course, we were finally able to start our Permafrost class, which was led by Marjolaine Ferret and Knut Tveit. They are both at the Department of Geology at UNIS, and Marjol is a postdoctoral researcher and Knut is a PhD candidate. And they were our course instructors. The course extended over 6 weeks, and we were a total of 10 PhD students and 10 master students, and we had a combination of lectures and fieldwork, and selected topics related to permafrost were presented to us, and we also had guest lecturers who are experts in their respective fields come and talk about their recent research. So a few basics for you to understand the key concepts that I will talk about soon is, as I'm sure that many of you already know, but permafrost is soil or organic materials or ice, even it's thermally defined, which means that the temperature of the permafrost stays below 0 for at least 2 consecutive years. So the permafrost is permanently frozen. And we have different types of permafrost. We even have it here in the Alps, which is the alpine permafrost. But up there, the only permafrost zone we have is continuous, which means that 90 to 100% of the area is underlain by permafrost. And on the right-hand side, you can see the permafrost thickness is right here. And here you can see the surface. And between the permafrost and the surface, we have this so-called active layer. And this is the layer that seasonally thaws and freezes, which means that in summer, the temperature will rise above 0 degrees. So this is the part of the permafrost which is not permanently frozen. And this is important to remember. So we have a seasonally thawed and frozen surface layer above the permafrost. I'm sure many of you maybe already heard about the Arctic amplification effect. This is a phenomenon that states that the Arctic warms up at a faster pace than the rest of the globe, 4 times faster actually. And this has a lot of causes, but the primary cause is an ice albedo effect and changes in the atmospheric circulations. So the albedo effect basically means that this ice cover, sea ice cover in the Arctic acts like a white cover that reflects the sun rays back into space. And if this ice melts, then we have less reflection happening because we have less of this white surface cover, which means that we have more warming and then we have less sea ice cover again. So this is a positive feedback loop. And that's why this is a primary cause for this Arctic amplification effect. So how does this influence permafrost? It does. The IPCC brought out a report in 2019, specifically about the oceans and the cryosphere in a changing climate. And they said that the permafrost temperatures have increased to a record high. And they say this with very high confidence. So what you see in the left graph is different data sets from the Arctic. So one is, you can see it here, it's from Siberia, Canada, Russia, and region A has some data from Svalbard as well. And all of these have a positive temperature anomaly, which means that the temperatures are rising. And on this hand side, you can see the projected permafrost area change under the specific IPCC scenarios. And we can also clearly see that the permafrost area is going to decline. So what does this mean? This means if we have increasing atmospheric temperatures, we have increasing ground temperatures, and this is directly related to permafrost because we learned permafrost is defined thermally. And with this permafrost degradation, we have a carbon release into the atmosphere, which in terms then increases the atmospheric temperature again. So we have this positive feedback cycle, and this leads to the active layer thickening. So we are going to lose permafrost. The permafrost is degrading, and the active layer, the seasonal layer of the permafrost system, is getting thicker. But why does this matter if we have a bigger active layer? It has a lot of local and global implications. And firstly, I'm going to talk about the local implications and then the global. So one of the causes and implications is actually infrastructure damages. If we have an high ice content in the permafrost, then this means that if this active layer thaws and in the summer months and heaves in the winter months, then we have this cycle of heave and subsidence, which means we have a potential damage and stress to the buildings. So all the buildings in Svalbard are on these poles to make sure that the influences of the active layer, this subsidence and this heaving process is not influencing the buildings too much. So we could actually go in one of those. They have a cover outside, but you can see the structure here is here, and we could have a look on it. But they are engineering challenges because the more ice content we have and the thicker the active layer is, this heave and subsidence that we see increases and therefore also increases the damage. On the left-hand side, it's not so easy visible, but you can see here the damage from the heave and subsidence, and it is way more pronounced here. You can clearly see this was one of the houses that we visited. And you can see the damages here. Another topic are geohazards. Like I already showed you, Longyearbyen is situated in this narrow valley with very steep slopes on the sides. So we talked a lot about geohazards, and the two I wanted to highlight are rockfalls and landslides. And for rockfalls, the permafrost can be a trigger factor because this ice that is in the permafrost kind of combines and holds the structures and the rocks together. But if this ice were to melt, then we have these bigger active layers. This kind of glue that binds the rocks together gets lost, and rockfalls are occurring even more. And for landslides, it's a bit different because then the permafrost acts as a precondition, which means if we have a lot of ice in the soil and this ice is situated right on top of the permafrost, between the permafrost and the active layer, and it stays there, it is usually stable enough. But then if we have a triggering effect, for example, a high precipitation event or snow melt in the springtime, then a landslide can happen. And this is exactly what happened in 2016. So they showed us, like Graham Gilbert, who was one of the guest lecturers, he showed us that in October 2016, the active layer was pretty much completely unfrozen because all of the summertime it thawed, and then right around October it was completely unfrozen. And it was fine like this for quite some time. But here in October, you can see we had a high precipitation event, and this led to a devastating landslide that destructed some infrastructure. This is the dockyard at the end of the village. And here you can also see the destruction of some houses. So yeah, this is really, really something to think about, these geohazards. Okay, so now we can say that ground ice content and the quantification of the ground ice content is important, but how do we do it? We have different methods available. And one of the straightforward ones is core drilling. You just go into the field, you drill a core, you take the core out, and you check how much ice content is there. So we did this. Here you can see Longyearbyen, and this valley here is called Advendalen, And this is where we did our drilling. So here you can see the engine of the drill and the core barrel. And basically you drill a hole into the ground and you take it out again. You extract the core from the barrel. You need to be very sensitive with this because you don't want the core to break, but it happens anyway. And then also you want to secure your core in sample bags. This is how it should go. Sounds easy, right? Except that it isn't, because this really gets stuck all the time. If you wait 5 seconds before drilling it up again, it can already get stuck because the ice is so powerful. And then you need some wrenches on both sides and need to go around to try to get this drill out again. So we needed some help, and we really tried for quite some time, maybe 20 minutes, 4 people to get this out. Nothing happened, so we need a little bit more help. This thing weighs around 4.5 tons. So you can see how powerful the ice actually is. And this is Uli. He is a German who has a drilling company out there, and he always goes out in the field with students, and he helped us out of this misery. So in the end, we only got to 140 meters of drilling depth, and our other team members, I think they got until 2.5 meters. But this was less work for us in the lab then, at least. So this is called a cold lab. There we went to actually analyze the core, which means that you lay it straight the same as it was in the ground. You put it there, and this is called cryostratigraphy. You try to find sections that look similar, and you put them in different bags, and you number them, and these are cryostructures. And once you have those samples, you can actually do an analysis with it and look at it and just try to strategize and categorize the ice content in this different categories. So for example, here it was very visible ice. We could see it here, and sometimes it's more lenticular or more pore ice, and then it's not so visible for the human eye. So how do we know how much ice is now in this core sample? It is a quite easy method. You just take the whole sample, you weigh it, and after you weigh it, you put it in the oven overnight to dry it, and then you weigh it again. And this is how you can infer the soil moisture content and therefore also the ice content. So this is what we did. This is a pretty straightforward method. But of course, you only have one point source measured. You have one in situ measurement. So if you want to upscale a little bit, we can use geophysics, which we also did. This is a method that is non-invasive, so you don't have to drill into the ground. And it is a bit more broader, so you can upscale your research a bit more. So what you can see here are electrodes, so-called electrodes, and a series of electrodes is installed into the ground and connected with cables. And then current is injected at 2 electrodes, and voltage is measured at the other ones. And then from this, we get the so-called electrical resistivity value that tells us about the subsurface properties. And this is generally speaking, it's way more complicated, but if we get high resistivity values, we can say that frozen ground is present, so permafrost is present, and that we have a ground ice content there. Low resistivities means presence of unfrozen ground, so for example, the active layer in the summer, or water-saturated soil, and so on. So here you can see us installing the electrodes. We had to drill a little bit because we need to put the electrodes into the ground and then connect it with cables. And this is after data processing. This is usually the imaging that you get. Blue, it means high resistivities, and red, low. And you can see here that actually no permafrost is present. And the frozen layer that we can see here, this is the frozen active layer because we went out there in winter time. So yeah, this is also a very good method to infer if we have permafrost or not. And if we want to go even further, we can use remote sensing. Of course, we couldn't try it out in the field, so we got some data and we played around it in the lab. But what they used here is, like, our guest lecturer, Line, she's a remote sensing. She's in the field of remote sensing, and she told us about her study. And what they used there is called INSA, which means Interferometric Synthetic Aperture Radar. And it is a remote sensing technique that basically uses radar signals to measure and monitor ground surface deformation with high precision. So basically, we have a satellite, and this satellite is monitoring the ground surface. But of course, permafrost is a subsurface condition. So we cannot only rely on remote sensing to say if there is permafrost or not. But if we combine these methods with other techniques or modeling, then we can already get to pretty good results. And also, we can map the ground for sufficient morphological evidence that there is permafrost present. So, for example, what I did here. Here you can see data from Sentinel-1, which is a satellite, from the 10th of June 2017 to December 2017. And what they measured basically is the distance from the ground to the satellite and back. And what they found in June to October is that the ground was moving away from the satellite, which means it was sinking in, it was settling, it was subsiding. And then during the freezing period, the ground was heaving up towards the satellite. And from this distance, you can kind of measure these onsets and offsets of this thawing and freezing period. So remote sensing is really good to fill in the gaps that we have between the core measurements. So if we have a research area and we do some core extracting drilling, for example, or geophysics, then we can combine it with remote sensing to get a bigger picture. So so much about the local implications. And now I want to talk a little bit more about the global implications that we can see. And I want to talk to you about the so-called cryospheric cap. Now I want you to imagine some sort of carbonated drink, right? And if you were to open this bottle, then there would be some gas release, which is fine. But I guess that all of you know that if you shake this bottle a little bit and then open it up, things can get messy. And if we want to use this as an analogy, then we can say that climate change is messing with our drinks and is shaking up the subsurface carbon storage quite a bit right now. This cryospheric cap, you can imagine as the bottom of the cap, and it is formed by the glaciers and permafrost together. I will tell you more about that soon. And we have a lot of carbon stored in permafrost. It is very uncertain how much, because it is very tough to quantify, but IPCC said it's roughly around 1,500 gigatons, and other sources say it might be a little bit less. But it is still a lot, because 1 gigaton is 1 billion metric tons. So there's a lot of carbon stored. And what we can see is these proglacial icings, which basically are like sheet-like masses of ice formed during winter when the surface water finds its way to the surface. So you can see the schematics here. We have some sort of discharge from the subsurface to the surface. This freezes, and then pressurized water is coming up again and it freezes again. And this is how these this is proglacial icings are formed. And in the past, we had the permafrost, and we had the glaciers, and they would really form this cover of the subsurface, and there was no way for the subsurface water, for example, groundwater, to get to the surface. But what happens with climate change is that the glaciers are retreating at a fast rate, and the permafrost is not fast enough, cannot aggregate fast enough to fill this gap up. So we have this little gap here, and this is called a talus. And a talus is an unfrozen ground within the permafrost layer. This can have many reasons. For example, if there is a lake and this lake water is warming up the ground, then you can have a talus between in the permafrost zone. And this is what's happening right now. So the water, the subglacial water, or for example, the subpermafrost groundwater finds its way out of the subsurface and actually discharges at the surface. And we have worked with two geochemists, Andy Hodson and Gaby Kleber, and they told us that they're trying to find out where this water is coming from. If it's glacial melt, for example, or if it's groundwater. So what they found out, and this is very recent research, is that actually it could be groundwater that is coming up to the surface And this groundwater takes methane from subsurface, takes methane which is stored in rock reservoirs, and also methane that is produced by microbes. The water takes this methane with it when it comes to the surface, and then it's released into the atmosphere. So this is the problem that they found, and they did a lot of sampling. They took samples from all the icings they could find. Here you can see the locations of these proglacial icings, and then they did some measurements. And what they found out is that every of these icings is a methane hotspot. The methane concentrations that they found there is more than 600,000 times greater than those that are in equilibrium with the atmosphere. So to put it in other words, it's 8% of Norway's annual oil and gas related energy emissions. So this is quite a lot. And they confirmed that by their study, which was just last year. So this is pretty recent. And how do they measure this? With geochemistry. It's also another method that we can use. And basically different water sources, for example, ice or snow or rain, have distinct chemical fingerprints because it depends with which kind of environment it has interacted. So for example, if this water was in some form of contact with the atmosphere, then we would see oxygen. If it was in some sort of geological layer, then it has this and that mineral trace. And so geochemistry tries to inversely deduct the flow path of the water. So we test this water and we try to find out where this water was flowing beforehand to finally understand the source of this water. For example, here, you can see here, the groundwater is quite shallow and this is quite deep groundwater. And depending on what we measure, what geochemicals we can measure, we can interfere if this is deep groundwater or shallow. For example, deep groundwater would be anoxic, so no oxygen at all, because it hasn't been in contact recently with the atmosphere. And then shallower water would have some dissolved oxygen content. So we went out in the field and we tried it. We drilled a hole again, and then there was pressurized water released due to the freezing, and we could just measure it right then and there. And as you can see, this water doesn't look that fresh, so probably it is groundwater. And like I said, they confirmed this in their recent research. And yeah, the release of methane has global implications for climate change, and this is why we should worry, because these methane hotspots are increasing. So for the end, I wanted to talk about some archaeology. And it was really interesting because we had a guest lecturer, and her name is Lise Loktu, and she told us about her field. And her field is archaeology, and it is also related to climate change and permafrost. So Svalbard is a group of islands, right? So we have a lot of coasts, and these coasts are also prone to degradation because the permafrost, if it's particularly ice rich, like you can see here, of course, if this water is, the storm waves are hitting this ice and ice and ice again, then it's melting and it is prone to rapid melt. And this is how whole coastal systems can collapse. And we can see the highest erosion rates in unconsolidated sediment deposits, which make up 65% of the Arctic coasts. So the Arctic coasts are really prone to erosion. And this has different implications for the marine systems, for the ecosystems, and also socioeconomic systems. Again, if there are houses close to the coast, then there are also infrastructural damages. But what I want to talk about is the socioeconomic impact in terms of archaeology. So Lise Loktu, she told us about archaeological sites in Svalbard, and there are around 4,300 registered sites. And she said that there are many more sites probably, but they are really poorly studied. So the number could be higher. And she did a study up here. And it was about preserved burial sites of Europe, of the European whaling period. So back then, 1600, 1700, there was a lot of whaling happening on Svalbard, and there are a lot of burial sites that are super preserved because of the permafrost and because of the cold temperatures. These graves are really well preserved. And they did some They did some excavation of these graves already. And in 2016, they actually excavated 3 graves that were prone to erosion. So they had to be quick because these graves were already really close to the shoreline. You can see it right there. And yeah, they excavated these in 2016. You can see right there is the grave and there's the coastline. So they had to be quick. And in 1985, there were already 14 graves excavated that were also at risk of erosion. So this was the first time since then that they excavated some graves again. And yeah, you can see the problem right there. The coasts are eroding in such a fast pace that the research is not fast enough. What they're trying to do, she told me, is that they really just try to go as quickly as possible into the fields to save these burial sites and to preserve them, because the knowledge found there can have completely new findings and implications for how we understand the whaling period, for example. And she said that there is an urgent need for more research, and also because of the thawing of permafrost, if the temperatures increase, we do not have this conservation effect anymore. If it gets warmer, then of course it is harder for the conditions to stay stable, and we're going to lose a lot of this cultural heritage and a lot of history if they don't scale up the research. So the take-home message there, I know this was a lot. You can imagine how much it was for us, the 6 weeks that we went there, is that Svalbard's climate is increasing drastically. I said 4-fold, but regionally for Svalbard, it is even 7-time-fold. Permafrost has many local and global implications, which I tried to show you and give you a little bit of an insight here. And there is a variety of geoscientific methods, which I also showed you, that we can use to try to understand such complex systems as permafrost. And what is also important, that the combination of these methods can help us to monitor and research these systems, and we need more interdisciplinary research. For example, Andy Hodson, the geochemist, he said he would benefit so much from a geophysical profile at his research area. So he really went to the geophysics department and said that they want to work together, because combining these methods can be really beneficial. So yeah, this was my talk about the course in Svalbard. And if you want to find out more, or if you're interested in going to the Arctic, you can scan the QR code here. And I thank you for your attention.